Good evening, guys. Yes, I know you're tired. We too, but this is the last group. Okay. We're gonna explain the same project, the same case study, and it's presented by Monsen, Drew, Olga, and I. The objective of the case study is basically applying concept of production science to this case. Solve the plant's shipment problems, improve the lead time from 5 days to 3 days, and improve the overall operation of the plant. Um, I want to highlight something before introduce and describe the project. This is one company that is right now one of the largest instrumentation and control companies in the world, and sells service and manufacturing operations in more than 80 countries around the globe. The product of concern is the model 88008, a smart vortex flow meter, and is used to measure the control of fluids and steam. One product can be made in hundreds of different versions and made to order, each meter configured for specific conditions. Now Olga is gonna describe the problem.
Basically, it's a process flow for the flow matter. And we have the plant is producing in a day like a job shop, and basically they're running by the day shift, but they have like a basic skeletal force during the night shift. Okay, we construct a Ishikawa diagram in order to generate all the root causes of our problem. We have a measurements, machine downtimes, scrap and rework, product mix on the flow labs, bottlenecks, and setup and adjustments. This is the flow lab configuration. In the in this chart, we can see each line and different sides of each product that we have to combine for magnetic vortex and the commune line between these two products. For example, in the line 4, 5, 6, and 7, we have a common product and a similar size for magnetic and vortex product. This is the production data. In order to verify the problem, we just calculate all production data. This is the shipment data, the current shipment data between the planned shipment data, and we can see that it's our shipment data. Our shipment is below the plan. This is the cumulative production data for the shipment. Drew will explain the flow lab process.
Good evening, friends. Basically, in this presentation, in the slides, we have just shown the various graphs. These all graphs were made based on all the calculation we did over here. For the first graph, if you look at this one, basically this backlog analysis we have just done for the 4 weeks, just using the data or this one for the 4 weeks over there. Then for the lab data, these are all the data which are given in the case study by the professor. So based on that, we did all the calculations. Sorry, not the calculations. Used all those data, and we made the flow rep run average mix, which tells us basically the different flow, the different configs of the flow meter running through there. And in this data, based on we calculate the availability based on the formula MTFF upon MTFF plus MTR. So we got the availability based on the availability. we could find the total time available for machine using number of hours per day or per week. Then we calculate the yield, and this is that chart shows the process yield for the various. Based on this, over there, we calculate over here the bottleneck rate, the throughput, and the weight. And here basically all the calculation based on for the different throughputs and the cycle time for the best case, worst case, and the practical worst case. Here we have not done based according to data. Here we just took the increments of 100 and we found out for all the things. The chart you see that very different from all the other presentation, because we just use the cumulative data for drawing the charts over there. Then in the analysis which we did, after finding the number of products produced over here in the column O, we found out the time taken for the production. Then using the formulas in the textbook and applying over here in this Excel sheet based on the columns, we found the various values for standard deviation, thus arrival rate, departure rate, effective process time, the capacity, RA, RB, and the utilization. And based on all that, we found out the cycle time for Q, the total cycle time, which is cycle time in the Q times the effective process time. After as we know the throughput in the cycle time, we can find the WIP based on the returns law. And also we found the WIP in the queue, and then we found the WIP in the buffer.
Everybody appreciate our work.
And again over here, we used in the increments of time for the various values and we found the throughput. And again, here we use again the cumulative data to draw the table. And this is over here. Here you see the bottleneck rate and the throughput and the WIP over there. Mossing is going to take the next.
Why? Are you starting today or tomorrow, right? Yeah, tomorrow afternoon.
So improvement and recommendation. First, reducing waiting time. Since we have some process had shared between two products from the same family, we need to set a separate process line for each product family. And the second one, we need to have better coordination between the different divisions. And the third one, we need to carry out maintenance at regular materials so we can reduce the mean time to fail. That's improvement.